One path toward building a secure quantum network involves physically tying beams of light into stable, three-dimensional knots. Photons are excellent carriers for quantum information. Because they are fast and typically move through the environment without interacting with it, they are primary candidates for the data-carrying backbone of a quantum internet. Today, we encode data onto these photons by manipulating their internal properties, usually their polarization or the specific spatial shape the light takes as it travels. However, these encoded states are incredibly fragile. Because the data relies on precise alignments, even a minor change in the local temperature or a bit of stray electromagnetic noise can shatter the state, destroying the information. Currently, the only way to protect these states is to house them in room-sized laboratories. As you can see on this optics table, it requires a forest of heavy, hyper-stabilized lenses and mirrors just to keep the light coherent. If quantum information requires this level of physical infrastructure just to survive ambient noise, a scalable global network remains out of reach. To solve this, we have to look at how light behaves in free space, the open environment where these properties are most vulnerable. The first property is spin-angular momentum. Think of this as the photon rotating on its own axis. The second is orbital angular momentum, which defines the spatial shape of the light as it moves around a central point. In free space, these two rotational properties operate completely independently from one another. They never touch and they never interact. This independence is the source of the fragility. Because they aren't linked, a disruption to just one of these properties is enough to cause the entire data state to collapse. Researchers have now managed to shrink this entire process down to a microscopic chip. Moving from an open table to a confined space, they've changed the environment light interacts with. The device consists of a gold film patterned with nanoscale features. These structures are smaller than the wavelength of the light itself. When a photon enters this near-field environment, it triggers ripples of electron density across the gold. At this scale, the electromagnetic pressure is so intense that the photon can no longer keep its spin and orbital properties separate. The near-field environment squeezes the two properties together, physically locking them into one unified state. This creates a single property called total angular momentum. Instead of two fragile pieces of data, the information is bound by a unified structural geometry. When this unified photon leaves the chip and scatters back into the macro world, it doesn't fall apart, it retains that unified structure. It emerges as a skyrmion, a topological quasiparticle that takes the shape of a complex three-dimensional knot of light. This structure acts like a form of armor. Because the information is encoded into the geometry of the knot itself, environmental noise cannot easily shatter it. The knot simply flexes and remains intact. Compare that to the old method seen in this archival photo. By moving away from massive optical benches and toward chip-scale devices, we solve one of the primary problems of scaling quantum technology. Engineers can now generate complex, resilient quantum states on mass-producible microchips, much like the ones found in modern electronics. Turning fragile light into topographical armor provides a way to protect quantum information from its environment, addressing a key requirement for the development of a future global quantum internet.